Good morning, everyone, and thank you, Etienne, Patrick, and Valerian for the invitation. And it has been a long trip, but I was really rewarded by your fantastic talks. And in return, I'm going to talk a bit about the technical aspects to explore the human cognition. Sorry, it's stuck. No, okay. These days, it's easy to get brain activation map like this. But an activation in this, sorry, I may have got this one. Okay. Yeah, activation in a particular region has been associated with a certain cognitive function. But this activation is the result of inputs from multiple brain regions. And this activation can also be the cause of activation in other regions. So to explore how the human brain works, it is really important to examine the neural signal transmission across brain regions. And there have been some sophisticated methods to explore the functional or effective connectivity using DCM, such things. But first of all, you've got to believe Carl Friston. And it has always been very difficult to understand what he's talking about. And actually, I thought about a much simpler method. In animal studies, people stimulate neural fibers and examine the postsynaptic potentials. And based on its amplitude, based on its amplitude, people estimate the efficacy of neural signal transmission, and which might reflect synaptic functions. In the human brain, we have only a very crude method to stimulate the brain, which is the TMS. And this technique stimulates millions of neurons under the coil. And we have very crude technique to record the evoked potentials. We have very poor temporal and spatial resolution. But still, we can estimate the direction of signal transmission from the stimulated region to other regions. And by examining the temporal sequence of neural impulse spread, we can talk about direct effect of the stimulation over the next region. Of course, here we are looking at the effects of artificial stimulation rather than physiological neural signals. But still, we can say something about the efficacy of neural signal transmission. And what's nice about this technique is that by giving stimulation at particular time points, at various time points during the cognitive performance, we can estimate the instantaneous state of the neural network when the stimulation is given. Now, we use TMS and EEG for recording the stimulus-evoked response. And here's the EEG waveforms on TMS trials and no TMS trials. And each color indicates the location of the electrodes shown on the scheme. And by subtracting one from the other, we obtain TMS-evoked potentials aligned at the onset of TMS. And based on these waveforms, we can construct the scalp topography. And also, from this scalp topography, we can estimate the cortical source of activation, which explain this topographic pattern. Now, here's an example. When we stimulate the frontal cortex with a single pulse TMS, the stimulation first induces activation in the frontal cortex and then spreads toward the posterior regions, moves back toward the frontal cortex, and comes back to the posterior regions more widely. And the number at the right bottom indicates the time from the TMS shown in milliseconds. So let me show you once again. Here's stimulation, and then moves backward, forward, and moves backward again. And this back and forth sequence of signal transmissions occurs in steps of about 10 to 15 milliseconds. So it goes frontal to the posterior, and then go back to frontal, and then posterior, temporal, parietal, and so on. And the important thing to use this technique is to obtain high accuracy EEG signals. And it's been very difficult to do so, especially in a very old lab like our university. So our lab is in a historic building at the University of Tokyo, and the word historic is synonymous with the word very old and shabby. And the electric power supply of our institute contains every sort of noise. And then we looked for a good experimental room and found a good place, which is the men's restroom at the 7th floor. So we invited subjects to this special experimental room and conducted experiments. Now, I'm going to show the study conducted in the toilet. Yeah, actually, that's the truth. And, well, actually, I examined the original plan of the building, and stupidly, the main trunk of the electric power supply for the toilet was independent from the others, from other trunks, so it's free of noise. But anyway, subject watched visual face image superimposed on a vertical grating, which is moving toward right or left. And the task is to judge the gender of the face image or the direction of the motion based on the task instruction cue. And we gave a single pulse TMS over the right FEF at 134 milliseconds after the target onset. And here's the time series of topographies. And you can see the difference between motion task and face task within the time window of 20 to 40 milliseconds after the TMS. And based on this scalp topography, we constructed a source image, and we found activation in the visual motion area, MT, and also fusiform face area here. And the activation in MT, here, important thing is it's not the baseline activation. It's the activation induced by the FEF activation, FEF stimulation. And induced activation in MT was significantly larger in the motion task compared to face task, whereas induced activation in the FFA was significantly larger in the face task compared to motion task. This might suggest task-dependent modulation in the efficacy of signal transmission from the FEF. And also, this signal transmission pattern was associated with behavior. When subject made quick response, there was larger effect of the task instruction cue. But when the subject was slower in responding, there was less difference between the two tasks. Of course, this might suggest that at the time of TMS, subjects were not prepared for the task, and it may take time to set up the task, and that causes the slowing of behavior. Now then, this technique can be used to explore the temporal dynamics of the signal transmission. In subjects performed perceptual decision-making task for a random dot motion. And we gave stimulation during the early or late phase during the decision phase. And the TMS both potentials were analyzed in a factorial manner based on the timing of TMS as well as the accuracy of the decision. So it's 2 by 2 factorial manner. And TMS evoked potentials after FEF stimulation changed depending on whether the stimulation was given during the early or late window of the decision phase, irrespective of the accuracy of the decision. By contrast, the evoked potentials after ventral prefrontal stimulation changed depending on whether the subject made correct decision. I mean, they are about to make correct or error decision, irrespective of the timing of the stimulation. This might be consistent with the notion that FEF might be associated with accumulation of evidence over time, whereas the ventral prefrontal cortex may be involved in the selection of task-relevant stimuli. Here, I've talked about the dynamic aspects of temporary changing aspects of the signal transmission pattern. But this signal transmission pattern can be persistent in some situation, unless the subject make actual some action. Unless subject make action, this network state persists over time, at least for 20 seconds. Now, I'm going to show you some data. Here, the subject performed pro-saccade or anti-saccade task based on task instruction queue. And we gave stimulation over the right FEF at 200 milliseconds after the task instruction queue. We thought that this TMS evoked potential changes depending on the task instruction queue, reflecting the preparation of the upcoming task. But the pattern changed depending on the previous task, the task that the subject had performed on the previous trial. This is the TMS evoked potentials recorded from the parietal electrode. And as you can see, the red straight lines and continuous lines and dotted lines. That means that when subjects had performed anti-saccade task on the previous trial, there's a larger negative potentials, irrespective of whether the subjects are about to perform anti-saccade or pro-saccade task on the current trial. Then, you might wonder, how can the subject perform the proper task? Because the transmission pattern continues to reflect the previous task. Then, we examine the event-related potential on no TMS trials. And the pattern of ERP changed depending on the current task. You can see larger negative potentials when the subjects were about to perform the anti-saccade task, irrespective of which task they had performed on the previous trial. And this dissociation between the signal transmission pattern and ERP can be shown more clearly on the scalpel topographies. You can see that the signal transmission pattern changed depending on the previous task, whereas the ERP changed depending on the upcoming task. So there is some dissociation between these two measures. And also, this signal transmission pattern was also associated with behavior. When the subject made quick response on a current trial, the signal transmission pattern was less affected by the previous task. Whereas, when the signal transmission pattern was affected by the previous task, the subject was slower in responding. Because this residual of the previous task set for the previous trial interferes with the performance on the current trial. Now then, let me talk about the direction of the signal transmission. If you think about region A and B, and if you stimulate a region A and examine the transmission pattern from A to B, and then if you stimulate region B, and then you can examine signal transmission from B to A. So we can examine and compare the signal transmission pattern between the two regions. And here we again use the perceptual decision-making task for a random dot motion. In this task, random dots pattern were presented, and these dots are moving in every direction, but some portion of the dots are moving in the same direction. And you have to say whether this coherent motion is rightward or leftward. But in some trials, there's no coherent motion, but still the subjects were forced to judge whether this is right or left. And you could imagine that this, the probability of making rightward motion is about 50%. But this behavior is shown to be affected by the decision on the previous trial. And we found that this decision biasing effect from the previous trial is larger when the subject had made decision about an ambiguous motion rather than when they made decision about silent motion. When zero coherence motion was presented on the previous trial, then there's higher choice repetition probability on the next trial. This might suggest that some endogenous decision-making rather than exogenously driven decision has larger biasing effect on the next trial. And this idea seems to be supported by the error trial analysis. When we present a low coherence motion, subject sometimes makes error. And error trial, erroneous decision can be thought of as being made by some endogenous noise or some sort of signal, internal signals. And on these situations, there is a larger choice repetition probability on the next trial. Anyway, there should be some biasing signals or changed, altered network state which persists from the previous trial to the next. So we try to examine this network status by applying TMS during the intertrial interval. And we first applied TMS over the right FEF and found that the signal transmission from the FEF to the medial parietal lobe changed depending on whether there's some decision biasing effects or not. There's a larger signal transmission effect. This is the time course of signal induced activation in the medial parietal region. And at 20 milliseconds, there was a peak of induced activation after the FEF stimulation. But this amplitude was larger when there was decision biasing effect than when there was not. We then next stimulated this medial parietal region. And then this again induced activation in the frontal area. But the magnitude of the induced activation did not change depending on whether there was decision biasing effect or not. This may suggest that some unidirectional change of signal transmission efficacy during the intertrial interval. And my idea is that when you make a decision about an ambiguous stimulus, then this could have been made based on some endogenous signals, because there's no meaningful exogenous signals. And these endogenous signals may come from some backward signals from frontal to visual areas. And this backward connection may persist during intertrial intervals, And then, again, on the next trial, when an ambiguous stimulus is presented, then you have to use the same circuit, which is being biased by the previous trial. And then you make the same decision. By contrast, when there was silent stimulus, the decision can be made based on the bottom-up forward signals. And this signal, signal may not persist during the inter-trial interval. So this does not affect the decision on the next trial. Well, that's the idea. But then, okay, so the midterm summary of the finding is that by applying stimulation of a particular brain region, we can show task-dependent modulation and dynamic change and association with behavior and history-dependent modulation. And its signal transmission pattern is can be dissociated from regional activation, and it can change in direction-specific manner. Of course, and well, my wild idea is that it can be used to make inference about synaptic mechanism in the human brain, but this may require some pharmacological studies and so on. And of course, this change in the signal transmission pattern may reflect the fact that different populations of neurons are more easily get excited. So depending on which populations are more sensitive to the stimulation, then signal transmission pattern may change. And other scenario could be that this signal transmission pattern may reflect the efficacy of signal transmission within the target region. But given that the TMS stimulates the afferent fibers coming into the stimulated region, then this signal transmission pattern may reflect the change in the synaptic transmission within the stimulated region. So there are many possibilities. But still, I think we can obtain some interesting findings. So I'm going to explore these techniques more. And finally, let me talk a bit about some cognitive aspects of this last study. In this trial, in this task, I talked about some endogenous signals being carried over to the next trial. Then we try to characterize these endogenous signals using computational model. The probability of making a right word choice can be characterized by the equation like this, which is determined by a decision variable. And decision variable has been usually termed as the sensory strength multiplied by the sensitivity factor. But here, this reflects exogenous component of the task. But here, we have added some endogenous factor, which we call choice estimate. That is the estimate of the likely choice to be made on that trial. And this choice estimate is updated every trial by the difference between the actual choice and estimated choice multiplied by learning parameter. Let me explain based on an example. So when there's no sensory signals, and right word choice is assigned a value of 1, and left word choice is assigned as a value of -1. And here in that trial, the choice estimate is something like 0.2, which is there may be 20% probability of making a right word choice. And then, because there's no sensory signals, the actual choice depends entirely on these endogenous signals. And then the subjects make right word choice. And then the brain somehow calculates the error between the actual choice and choice estimate. and multiplied by a learning parameter and shift this choice estimate to this way. And this, and again, on the next trial, if there's no sensory signals, then the subject choice should depend on this updated choice estimate, and then subject makes the same decision. And if you repeat the same thing over and over again, then there's higher tendency that the subjects repeat the same thing over and over. And that's actually the case. If you look at this point, as the number of the choice repetition increase, there was higher, larger probability of the subject making the same choice. And here, there's motion, no sensory signals. But if there is some sensory signals, then the choice behavior depends on these strong sensory signals. And then it's become quite independent. Contribution of the choice estimate becomes less. And then the choice repetition probability becomes less. And actually, we have tested various kinds of models, including some modularity factor to the sensitivity or general choice bias and so on. But these all models fail to account for the decision bias effect. And we also try to model the sensory estimates or some other sorts of models, but all these models failed to account for the decision biasing effect. So the only surviving model is something like that. But as you can see, there's some similarity to the reinforcement learning algorithm, as Max has talked about. But the important thing is that, here in this task setting, there's no feedback for every trial. Subjects simply repeat the decision about the random dot motion task for hundreds of trials with no feedback. Well, in the reinforcement learning algorithm, then there's choice outcome or reward. And subjects use this information to update the prediction. But here, if there's no outcome or teaching signals, then subjects may seem to use their actual choice to update their own likelihood of the next choice. These are very stupid things. If you made errors, then he believes that this erroneous response as the real thing, and then to update the knowledge about the outside world. But the similar thing can happen when you make this, when you make a choice between the items with similar preference rating. When there's item A and B with similar preference rating, and if you choose, and you are forced to choose one out of two, and if you choose item A, then the next time around, the preference rating of this item A becomes increased. So their own action can be used to update the knowledge about the world. Of course, you may say that this is a kind of special situation when there's no feedback and you have to repeat the same thing. But this actually happens in everyday life. When you have to go make a choice between the French restaurant or sushi shop, and then you've got all sorts of information about the distance or your hunger level and the dinner last night and so on. But, well, you've made choice to go to sushi shop. But, you may have enjoyed the food, but you don't know. You could have enjoyed far better for the French restaurant, and there's no, in a sense, there's no actual feedback to compare between the two choices. But still, and if you find that this sushi restaurant is good, then you repeat the same choice again and again. So, well, anyway, that's an interesting part of this cognitive side. And I have I have been trying to do various sort of things using this stimulation and recording technique. One thing I'd like to show is that this cortical stimulation and recording technique, we have access to some neurosurgical departments, and well, as you know, in a passive listening condition, there's higher gamma activity in the auditory area, of course. And when subjects speak up and then listen to their own voice, there's suppression of its auditory response. And then, well, this has been associated with some sense of agency and some sort of stuff. But then well, in the next condition, subjects listen to their own voice. And before the onset of this recorded voice, we gave stimulation over the Broca's area using cortical microstimulation, cortical stimulation. And then there was reduction, suppression of auditory response. And this stimulation effect was temporally specific. When this stimulation was given at about 100 milliseconds after the auditory stimulus onset, then there's reduction in the response. And interestingly, only 1 out of 4 subjects I have tested, he said that I'm speaking. But I wanted to show some, I'm not quite sure about whether this patient understands the task quite well. So we need to do a lot of studies, so experiments. So it's still ongoing. Yeah, but it should be a nice thing. Anyway, my desire is to obtain some mechanistical biological understanding of how the human brain works. And it also applies to the higher human cognitive functions. It should be described in terms of mechanistic or biological manner. And then this could bridge the gap between the human brain or animal experiments, I think. Okay, so that's it. Okay.